So what do we have on the single line diagram? We have a 3-phase generator, 2 of them actually, and they are rated at 200 MVA, 13.8 kilovolts. They have a reactance of 0.85 and are generating 1.15 per unit, each of them. So next up we have a step-up transformer, T1, with its values. Then we have the transmission line. Then we have the step-down transformer and the load. What do we need to do? We need to convert all these quantities to a common base of 500 MVA and 220 kV on the line, and draw the circuit diagram with values expressed in per unit. So here is the circuit diagram, and the values in pink is what we have converted to the new base, everything in per unit. So how do we do this? The generators here, we know they are generating 1.15 per unit, so we need to find out the new per unit based on this new base we're using. Then from the generators we're going to have reactance for each of them to calculate. Then bus bar and transformer. Once again, we can have a reactance to calculate here. Bus bar, line. We're going to have another reactance to calculate for the transmission line. And then step down transformer. Here, once again, another reactance. Bus bar. And for the load, we're going to have a resistance and reactance. So we're going to have an impedance. We don't have a resistance for the generators. We could have, drawn another one like this. So we can say they are ideal generators. Anyway, let's start. So what shall we find first? Let's find the reactance for the generators. So green. Here's a very useful formula we're going to need. So the impedance per unit, the new one, based on the new base we're using, can be found from the old impedance in per unit that we are given, in this case 18.5, and then multiply by the new base we are given to be 500 MVA over the old base, old, new, and then times by the base, the old base for voltage, base new, and square. So what's going on? We have, for the generator, we only have a reactance to find, not the whole impedance. But we know that impedance is resistance plus reactance, which is the imaginary part. So basically, ZR plus JX. We don't have this. So this is simply this. So instead of Z, we can just write X. So we can find the new reactance in per unit from the old reactance in per unit, which we know was from here 0.8. Yeah, so 0.8 times by the new base. What's the new base? 500. And what's the old base? The old base at the generator, 200. So 500 over 200 times by, now for voltage, what is the old base? 13.8, and the new base is going to be 13.5 in this region we're using. Because then we have another region and another region. So we have 13.8 over 13.5 squared. Now all of this gives you the reactant in per unit, the new one, to be 2.2 per unit. So you see here we have 2.2 for each generator. What else can we find from the generator? We've done the reactants. We can find the new voltage, the new generating in per unit at each generator. So this is the old one, and we're going to find the new ones based on the common base we're going to be using. So how do we do this? Voltage new is going to be the old voltage times by, once again, the old over the new, because we just have a ratio. So the old one we said was 1.15. It's already in per unit, so here we have the per unit ones. 1.15. And then the ones that aren't in per unit, the old one is, the old one is 13.8 and the new one 13.5. These are in kilovolts. We want to find, this is the old one in per unit, we want to find the new one in per unit. So we're going to have 13.8 over 13.5. This gives you the new voltage in per unit to be 1.176 per unit. My mistake, I wrote it wrong, but these are the ones. Okay, next up, what do we need to find? Let's move to the step-up transformer. So I'll go on and I'll just delete this actually. Okay, so for the step-up transformer, once again we can apply the same formula. So you can say that the new reactance in per unit, it's going to be the old reactance in per unit times by the S base new S base old times V base old V base new squared. Very useful formula to remember. So for the transformer, what are old reactants in per unit? 8%. And 8% is 0.08 times by what's our new base? Our new base, 500. And our old base is also 500. So it's just going to be 1, but 500 over 500. Now, for the voltage, what's our old voltage? Our old voltage was 13.1 and 13.5, and our new voltage is also going to be 13.5 because we're using that as our base. So 13.5 over 13.5 squared. This is 1, this is 1, so we just have 0.08 as the reactance at the transformer. Now for the transmission line. This one's going to be a little bit different because we're not going to be using this formula, because for the line it's not really defined by the equipment ratings but by physical characteristics. So let me delete this for the line, we're going to be using something else. So we can find the reactants, which is what we're trying to find, in per unit, the new one, but whatever, by the actual reactants we have, times by the base, divided by the voltage base squared. Now, how do we actually get this? We know that the reactant in per unit is the actual reactants divided by the base for the reactants. Do we know any of these values? Yes, we know that the actual reactants is 220. But do we know the base for the reactants? No, but we can find it. So X base is the voltage of the base squared over the S base. Very useful formula once again. We know the voltage base is going to be for the line, what is it? 220. And the S base, common base, 500. So we can simply do 220 squared over 500 and you get 96.8 for X base. So 220 over 96.8. This is going to give you hold on a second. No, sorry. The actual reactance we have is not 220. Sorry about that. It's not 220. The actual reactance we have is 7.8 and it's given in ohms. So 7.8 7.8. So now we're going to do 7.8 over 96.8 and we should be getting 0.081 per unit, which should be the same as this if you plug in the values, 0.081 per unit. Yeah, so 0.081 per unit. Now, what next? We have for the step-down transformer. Rubber. Okay, so for the step-down transformer T2, we can use the same formula as previously. So it's, we can do it as a ratio actually. So the new reactance, it's going to be the old reactance times by the base new over the base old. So what is our old reactance? Old reactance here is 11%. So that's 0.11 times by what is our new base? The new base is 500 and the old base is 400. So 500 over 400 and we get 0.1375 per unit. So basically this, 0.138. Basically just ratio between the reactances and the bases, because we're looking at transformers. And finally, for the load, we're going to have a bit more to do. So for the load. First, we're going to have to find the real power, so P, for the load in per unit. So that's going to be what we have for the load and what we have for the base. For the load, we have 250 MVA, and for the base, 500 MVA. So it's going to be 250 over 500, 0.5 per unit. How can we use this further? We can use this to find the power of the load as what we have here in per unit times by the power factor. What's the power factor here? Cos theta, which is 0.85 lagging. So what did we say it was? 0.85 times 0.85 is going to be 0.425 per unit, and this is your cos theta. We know that cos theta is, what's cos theta? The real power over the reactive power. And we can draw also this triangle. Reactive power, real power, and the apparent power. And what else can we find? So we found the real power here. Not this. So we found the real power. And what else we want to find? The reactive power of the load. So QL. This is going to be, once again, 0.5, which we found here, per unit. And we're going to multiply it by, this time we need to do sine theta. But what is theta? We can find theta by doing cos minus 1 of 0.85. Because cos theta is 0.85 and we want to find theta. So theta here, let's fill this in. Where's my rubber? Cos theta is the theta is going to be what we just said. So cos minus 1, 0.85. This is just theta that we're finding. And then once you do this, you're going to get, what are you going to get? 0.263 per unit. And what else do we need to find? The impedance of the load now. So the impedance of the load is the voltage per unit divided by the real power per unit. What is the voltage per unit? Voltage per unit. Well, we know we have at the load 33 kilovolts and on the other side in our part 33 kilovolts. So 33 over 33 gives 1. So we have 1 per unit for the voltage. And the real power, we calculated already, 0.5. Yeah. So you're going to get 2 per unit as your value here. Right. But what we actually need to find is the, let me rub. Okay, so what we actually want to find now here is your resistance and reactance from the impedance. So it's going to be the resistance of the load. It's going to be Z cos theta. Remember the triangle. So 2 times by 0.85, because cos theta is the power factor, and that gives 1.75 per unit. That's the real part. Now let's find the imaginary part, so the reactance of the load. It's going to be Z sine theta this time. So we did this last time. We found theta, and then you just put sine. So you're going to get 2 times 0.526 equals 1.053 per unit. That's your imaginary part. And here you go. That's basically it. And you know that Z equals ZL for the load equals the resistance of the load plus the reactance of the load. Real part, imaginary part. And yeah, that's basically it.